Okay, well, thank you all for joining us so early this morning. I certainly know that after a big night last night, I found it hard to drag myself out of bed in time to be here, but the excitement of hearing about these two amazing papers was enough to get me up and get me going. So we're here for the 2025 ACMC KDD Test of Time Award papers. A committee of us met to consider for the research track papers published in KDD in 2015, 14 and 13 and accepted nominations from those years and also looked at the most cited papers from those years to give us further breadth of the field. So there were around 20 candidates that we considered and we looked at citations as an indicator of academic impact, but also looked much more broadly at evidence of impact in terms of changing research in the field and also real-world impact. And there was a very, very clear front runner for both tracks, but for the research track, collaborative deep learning for recommender systems has been a very influential paper. Authors Wang, Naiyan Wang, and Dit-Yan Wang. Wang is going to present the paper now. The idea of these presentations is to explain the context in which the paper was written, because a lot has changed in the past 10 years, to explain what the paper was about, and then to also discuss the impact that it's had in the intervening years. And to do all of that in only 25 minutes. So a bit of a challenge for such impactful papers, but I look forward to seeing your presentation. So Wang, please join me in welcoming Wang to the stage.
Thank you, Jeff, for the wonderful introduction, and thank you, KDD, for the recognition. I also want to thank my incredible co-authors and collaborators, Naiyan and Dit-Yan, and many researchers who has built on our work in the past decades. We have taken deep recommender systems to places we have never imagined. I'm very excited today to present this award talk on behalf of the team. Published in 2015, our collaborative deep learning, or CDL, is one of the first deep learning recommender systems. So what is collaborative deep learning exactly? First of all, what is collaborative? Some of you may think that collaborative means additive learning. Actually, it has nothing to do with additive learning. Here, collaborative refers to collaborative tutoring. And specifically, it's a variant of collaborative tutoring called low-rank matrix factorization. And deep learning here refers to end-to-end deep learning of compact and user and item features. So to unify them two, our CDL jointly perform collaborative tutoring and deep learning of user and item features. So just to understand CDL better, it might be interesting to think about the problem we saw in 2014. That's 2 years after the ImageNet moment. Basically in 2012, Hinton and his team developed AlexNet that cut the ImageNet error rate by half, effectively starting the deep learning revolution. According to the economists, suddenly people started to pay attention, not just within the AI community, but also across the whole technology industry. However, at that time, existing deep learning, they are quite limited actually. They only work for simple classification and regression tasks. For example, given an image, classify whether it's a dog or a cat. It's therefore not very clear how to perform recommendation using deep learning. Now, for those of you who are not very familiar with recommendation or recommended systems, the problem setting here is that we are given a rating matrix which indicates what each user likes or does not like about each item. And then recommendation is simply a problem of matrix completion. Basically, we're given the observed preferences from users to items, and we are charged with the goal to predict the unobserved preferences. And usually, we're also given the content of the items, for example, movie descriptions, to help us improve the recommendation performance. Obviously, this is very different from simple classification and regressions, therefore not very clear how we can use deep learning to perform recommendation. I mean, sure, it's probably easy. In hindsight, but 10 years ago, it's not that obvious. So we, in the beginning of 2014, we took a step back and started to think about the fundamental limitation of early deep learning. And then we realized that there were actually two classes of tasks, two major classes of tasks in AI. And the first class would be perception tasks like video object recognition. And deep learning is particularly good at this kind of task because it can naturally and efficiently handle high-dimensional signals like text, images, and videos. And the second task would be inference and reasoning tasks. Right? This kind of task, it involves a high level of intelligence, decision-making, data analysis, and logic deduction. And there's this class of models called probabilistic graphical models that are particularly suited for these kind of tasks because they can naturally handle complex relations, conditional dependencies among different random variables. For example, this particular graphical model here tries to reason about the rating that user I gives item J, given user I's latent vector and item J's latent vector. However, typically, graphical models cannot efficiently process dense high-dimensional signals. So if we plot it in the figure, we can see that deep learning is here. It's good at perception, but not very good at inference and reasoning. On the other hand, graphical models, they are good at reasoning, but not so much on perception. However, in practice, these two classes of tasks, they often entangle with each other. For example, you cannot really accurately reason about the complex relations among two articles unless you can understand them separately. Therefore, it's actually desirable to combine the power of deep learning and graphical models into a single principal framework to get the best of both worlds. And to achieve this, we developed this new framework of hierarchical Bayesian deep learning. And in our framework, we have two components. We have a deep component, which is usually a probabilistic deep learning model to handle the perception. We have a graphical component, which is usually a probabilistic graphical model to handle inference and reasoning. For example, in movie recommender systems, the deep component will handle the content understanding of the movie. For example, movie descriptions, videos, plots, actors, and the graphical component will try to analyze the preferences and similarities among users and items and perform the actual recommendation. Now, on one hand, better understanding of the movie content can actually improve the recommendation performance. Right? This is natural. And on the other hand, better analysis of users' preferences and similarities among items can actually, in turn, improve the understanding of the movie content. And our framework formally can be represented using a larger graphical model where the deep component and the graphical component connect to each other to enable information exchange. And in the context of our collaborative deep learning or CDL, this deep component will be a probabilistic deep learning model to process the movie descriptions, and the graphical component will be to handle the relations among users, items, and ratings. Our CDL model, it starts from a probabilistic autoencoder where this X2 here is the middle layer representation, and internally it's actually just a probabilistic autoencoder. Right? For those of you who are not very familiar with autoencoder, it's actually very commonly used to extract features in an unsupervised learning manner. Essentially, it's just a feed-forward neural network where the content information, like movie description, will go through several layers of linear and nonlinear processing to reconstruct the content itself. And usually, the output of the middle layer will be used as the representation of the data. And following graphical model convention, here we're going to use shaded circles to represent observed variables that are given, and latent variables, we're going to use transparent circles to represent them, and also parameters to learn. And J is the number of items. Now with this X2, as the middle layer representation, we're going to generate the latent vector for item J from a Gaussian distribution centered at X2. The difference between X2 and VJ is that this X2 is the item embedding based only on the content, for example, movie descriptions, and VJ is the item embedding both based on both content and user preferences. So you can see that this VJ is actually more relevant to the recommendation task. And similarly, we're going to generate the latent vector for user I from a Gaussian distribution with zero mean. And finally, we can generate a rating that user I gives item J from a Gaussian distribution center at the inner product of their corresponding vectors. So you can see that the blue part here is the graphical component that describes the conditional dependencies between the users, items, and the ratings. Right? And based on this generative process, it's probably it's kind of like an inductive bias, and given the movie descriptions, the observed ratings, we're going to infer the user vector U, item vector V, and then use them to predict the unknown ratings. This is the overview of our method. These lambdas are just some hyperparameters to control the variance of the Gaussian distribution. Just to recall that we have a deep component and a graphical component in the Bayesian deep learning framework, and correspondingly, the probabilistic autoencoder is our deep component, not the internal, it's just the autoencoder, and this blue part is our graphical components. And these two components are going to be trained end-to-end to boost each other's performance. And specifically, the deep component can boost the graphical component's representation accuracy, and the graphical component can boost the deep component's representation learning. To see, besides this graphical model perspective, we can also see it in the neural network perspective. And specifically, if we set all these variance to 0, then our method is simplified into simultaneously training two neural networks with a common input but different outputs. Since the interaction is two-way, the information will flow from the ratings to the content, which means that the representation is actually adapted for the ratings. The information also flows from the content to the ratings, which means that the adaptive representation is actually used to improve recommendation. So to summarize, representation learning and recommendation can actually benefit from each other. And to see how CDL works, let's take a look at its simplified version. So on the one hand, this movie content, for example, movie descriptions, is going to go through an autoencoder to reconstruct itself, where X2 here is the item embedding from the content. And on the other hand, we're going to factorize this rating matrix into a user matrix and an item matrix. Note that for each row in the user matrix, it's going to represent one user's embedding, and each column in the item matrix, it represents one item embedding from the ratings. We call it VJ. So now we have two versions. Right? For each item, we're going to have two versions of embeddings, and we're going to push them together by minimizing the L2 distance between them as a sort of like an L2 regularization. Now let me remind you that we have two components. We have a deep component, which is actually the autoencoder. We have the graphical component, which is the matrix factorization. And to learn CDL, we're going to have to alternate between updating the deep component and the graphical component. Basically, we can update autoencoder while also performing matrix factorization. Specifically, to update the deep component, we're going to minimize the reconstruction loss, but at the same time, we're going to fix the item embedding from the ratings, VJ, and then we're going to minimize the regression loss, an additional loss, which is between the middle layer representation S2 and Vj. So combining them two, we have this objective function to update the deep component or the upper component. To update the graphical component, we have to perform matrix factorization. But at the same time, we're going to fix the other embedding from the content. This time it's x2, and then we're going to minimize the L2 distance between x2 and Vj. So basically, overall, to update this graphical component, we will need to perform regularized matrix factorization. And to evaluate our method, we use 3 data sets, 2 from SciUlike and 1 from Netflix. For SciUlike, we use titles and abstracts of the articles as the content information. For Netflix, we use movie descriptions. And these are some of the empirical results. So the horizontal axis shows the number of recommended items, and the vertical axis shows requirement. Higher the better. So you can see that the best baselines at that time are CPI and deep music. And our method can outperform these baselines by a large margin. Note that this is already a significant improvement, and the margin gets even larger when the ratings are sparse. So why would this happen? This is because when the ratings are sparse, the model's performance relies more on the quality of the representation of the content information, which happens to be the advantage of our method and of deep learning. And as a follow-up to CDL at Unrest 2016, we kind of developed a fully generative model, sort of like a fully generative version of CDL to jointly perform recommendation amongst all the requested text generation. And this is achieved by replacing the fully connected layers with recurrent neural networks. We also developed a new attention mechanism to aggregate variable length text into fixed length embeddings. And in hindsight, our large language modeling mechanism is kind of similar. It's developed in Unrest 2016. It's kind of similar to the popular Bert paper 3 years later at ACL 2019. So if you take a look at the timeline here, this is the ImageNet moment, and this is a free image network, and these are the post-image networks. So what happened since? After CDL, there are many interesting works from different groups. For example, collaborative knowledge-based embedding from Microsoft and visual VBR from UCSD. Specifically, in this collaborative knowledge-based embedding from KDD here in the next year, 2016, the authors substantially extend CDL to handle different modalities in knowledge bases, including graphs, text, and images. For example, to handle images, they kind of replace our Bayesian autoencoder in CDL with a Bayesian convolutional autoencoder to process the images. Another interesting work is collaborative variational autoencoder, or collaborative VAE. In this work, the idea is to replace the probabilistic autoencoder with a variational autoencoder. And by doing this, it can basically make the model more robust to noise, therefore achieving better recommendation performance. And in terms of generative model, in the same year, Julian's group from UCSD developed DBVBR. This is a very interesting work that can jointly perform recommendation and design with generative image models. Typically, recommender system, we know it will first infer the user's preference. For example, this user may want a purple dress, and then from the data set, the model will then retrieve existing clothing as personalized fashion recommendation. In contrast, this work uses GAN to directly synthesize new clothing as personalized fashion design. And the hope is that this generative design can better match the user's preferences. And in some sense, this is quite similar to our generative recurrent CDL, which jointly perform recommendation and text generation. The main difference is that they replace the RNN with the GAN model to generate images. So far, all of this work, they use both content information and the rating metrics. And in 2015, our hypothesis is that content information is intrinsically hierarchical and low level, therefore it has to rely on multi-layer neural networks to extract high-level features. In contrast, rating information, it already captures high-level semantics, and therefore linear models like matrix factorization mostly suffice. Now, 10 years later, we now know for certain that this first part is true, but the second part is still very much an open problem. So naturally, a very interesting direction to explore is deep recommended system without content information. And along this line, an important work is neural collaborative filtering, or NCF. And the idea of NCF is actually quite straightforward. For each user item pair, we only need to concatenate their user latent vector and item latent vector and send them into the neural network to predict whether this user likes this item. And by comparing CDL and NCF, we can see that CDL uses nonlinear transformation for item content, but linear interaction between users and items. In contrast, NCF, it has no support for item content, but uses nonlinear interaction between users and items. Besides NCF, maybe several other important works, including VAECF, which was developed by Netflix. Basically, what they do is they replace a neural network, regular neural network with a VAE. Another important work will be hierarchical ironing by Amazon, which wins the KDD 2020 Best Paper Award. And so far, you may have noticed that deep recommended systems already have a huge impact in the industry. For example, this collaborative knowledge-based embedding was developed by Microsoft, and VAECF was developed by Netflix. And to the best of my knowledge, they did observe significant improvement in their system, and they deployed this system in production soon after that. HRNN is actually the backbone of Amazon Personalized, and it's a recommendation API which has been deployed in companies like HBO, Fox, Saraf, and Intuit. Google also developed the wide and deep model for recommended systems and deployed it at Google Play, Google's App Store. The idea is to use a linear wide model to handle the binary features and feature interactions, for example, a combination of gender and language, and then use a nonlinear deep model to process the sparse features, for example, the user's installed application. A similar model was deployed at YouTube. Besides these companies, there are also other companies developing their own deep recommender systems, for example, Airbnb, LinkedIn, Meta, and Twitter. So what's next? In 2020, GPT-3 was released, and in 2022, we had the ChatGPT moment. So around that time, we started to think what language models can do for recommender systems. And it kind of occurred to us that they can actually enable zero-shot recommender systems. So specifically, we developed ZSREC, or zero-shot recommender systems. And in this system, so each item, its text descriptions will be fed into a pre-trained language model to generate the item embeddings. And all of these item embeddings will be fed into a sequence model, for example, a PRE or transformer, to generate the user embedding. And by comparing the user embedding and candidate item embeddings, the model will then recommend items to this user. So you can see that everything here is grounded in natural language with the language model. Essentially, we're using language as a universal item ID here. And by doing this, we're going to enable zero-shot representation for both new users and new items. And following ZSREC, we actually go even further to directly use an LM as recommender system. So specifically, given an LM, we're going to feed the movie descriptions into the LM as the knowledge, and list the user's watch movies using natural language, feed them into the LM, and then the LM can reason about the user preference and generates the movie names, token by token. So what's next? After ChatGPT was released, our ZSREC and LM references started to make sense to people, and suddenly there were many works on LM for recommender systems. And one interesting work is LM to Bert for RAC, is an improved version of ZSRAC. One improvement is that for the sequence model, they replace GRU in ZSRAC with a transformer. Another improvement is for the embedding model, kind of replace the Bert model in ZSRAC with OpenAI's text embedding. Another interesting word is co-LM, which incorporates collaborative filtering information into LM. It uses Pecunia 7B as the LM, and then computes the user and item embeddings from collaborative filtering, and then feed them into LM, and then fine-tune the LM with LoRa. So just to wrap up, where we headed in the next decade, we're seeing a shift from task-specific recommenders to general recommenders based on foundation models and agentic models. In the past, recommender systems, they are typically optimized for one specific domain, movies, music, news. But now we're starting to see general purpose recommender systems that can reason over diverse domains. Like ZSRAC, we expect zero-shot and few-shot recommender systems to become the norm. And the goal is to recommend items with no or few interaction history, or even just a single sentence of natural language input. We also expect a tighter integration between recommendation and generation. Just as we saw in early works like PVPR and Unrest, future systems can not only recommend existing content, but also generate personalized new items, for example, new movies or new music. Finally, generation, it kind of introduces new risks as well, including hallucination and toxicity. Therefore, these risks call for robust guardrails to ensure that the generated outputs are both relevant and safe. And last but not least, I would like to thank all my students, collaborators, family, and friends for their support. And with that, I'll be happy to take any questions. Thank you.
Wow, a decade of recommender systems in 25 minutes. Very impressive feat. Thank you very much. So we have time for questions. So just to clarify, the presenters were told to give 25-minute presentations, but being given a 90-minute session. So we have time for a few questions.
Thank you so much. My question is about the early slides that you have for experience and perception and your recommended Bayesian
I think that's a good question. I think I can answer this question in two parts. First of all, to repeat the question is about the Bayesian deep learning, the hierarchical Bayesian deep learning framework that we have, and the question is that the framework kind of bridge the gap between perception and reasoning, and why not use reinforcement learning to bridge the gap, right? Instead of using this framework. And my answer is that we have two parts. Now, I guess the first part is at recommender system, we at least in the very first version of the recommender system, we're not dealing with this long-term feedback or delayed feedback in recommender system. We're tackling the cases where we have the previous ratings and then we'll predict the future ratings, and it's like immediate future ratings. So in this sense, I guess our framework will suffice. But that said, I think it would be very interesting to kind of incorporate this reinforcement learning mechanism to deal with even that longer-term feedback in the loop, right? Right, exactly. Actually, some of our work involves bandit problem as well, and you can think of the bandit problem as you have this. Actually, it involves a neural contextual bandit. You can think of the bandit problem as we have this deep component to process this dense sparse and high-dimensional content information, and you have this little header to handle the uncertainty, right? For example, upper confidence bound or Thompson sampling, and this had to handle this uncertainty and recommend in face of uncertainty. And this hat, you can think of it as a simplified version, right, of the graphical component. You can even incorporate even more nuance, like domain knowledge and conditional dependencies into that as well. Yeah, thank you.
Yes, so we're recording the session, so if you have questions, please go to the two microphones.
Thank you very much for this overview of the past decade. It's very helpful. My question is, you didn't mention that much about sequential recommendation, and how does that fit in this framework, and how would that be kind of improved, enhanced with this large language model techniques?
Thank you for the question. I guess by sequential model, you mean the RNN and transformers, right? And
I'm more of talking about given the time series of what the user has done, has visited, has purchased, predicting the next item, but keeping the timeline in mind and give it more emphasis.
I see. Yeah, that's a good question. I guess that would fall into our ZASRAC talk, right? ZASRAC part of the talk. You can use, again, you can still use an RNN or transformer or a time evolving version of that to handle the temporal information that you mentioned, right? And you can even, if you want to add more domain knowledge into the model, you can use the graphical component to handle it. Right. So I guess that is kind of very natural and will be very interesting direction to pursue in the future. Thank you for the question. I'm not sure if this answers your question, or do you have any follow-up? Thank you.
We can take one more question if anybody wants to. Last one.
Maybe a question about the representation of the content versus the representation of the interactions. So in CDL, you sort of have this iterative update scheme that brings these two into some kind of alignment in a way that is probably viewed best as sort of a prior on the representation that comes from the interaction data. The other schemes maybe represent some embedding of the item and the users directly for kind of standard gradient descent against the final loss, as opposed to something that's more probabilistic or interpretable. Do you have a sort of guess or an intuition for whether the content and the interaction information should be aligned in some way in future systems, or should be kind of separate parts, and whether they should be trained against a single loss versus these type of iterative approaches?
That's a good question. CDL, it's kind of a very early version and very early exploration of that. And I do believe at least there will be some benefit in terms of jointly consider the content information and the interaction information and consider the interaction between the two as well. So it's kind of like an open problem. And I guess one related work to the open problem is someone did some kind of preliminary study comparing purely linear matrix factorization with a neural version of the matrix factorization, and they do not see a clear improvement of the neural version upon the matrix factorization. So I guess this is kind of an open problem. But on the other hand, I think industrial systems that matters, I think it's called DLRM, they do observe some benefit in terms of incorporating very highly nonlinear interaction between the content and the rating information. They basically build a very, very deep network and a lot of interaction, and they kind of improve, they're shown to improve the performance. So I guess that would be an interesting direction to explore to further further shed some light in this field. Yeah.
Thank you, Hao. So now can I ask you all to join me in warmly thanking Hao for a fantastic presentation and Hao and his colleagues for an amazing contribution to the field of recognition. Thanks, everyone. To come and set up. So the next presentation is for the test of time for the applied data science track. Do you want to set up rather than while I talk? So this award is considers the papers published between 2011 and 2015 in the applied data science track. And again, we took the nominations that we received, as well as considering the most cited papers. Is there a problem with connecting? Do we have technical support? Nice. And again, there are many strong papers you can imagine from a field of 5 years of KDD, but this work stood out as being particularly influential. The winner of the Applied Data Science Test of Time Award goes to Beating the News with EMBERS, Forecasting Civil Unrest Using Open Source Indicators, published in KDD 2014. I will not list all of the authors because I want to leave at least a bit of the 25 minutes for Naren to complete his presentation. So it's by Naren Ramakrishnan and many co-authors. So a very big team produced a very impressive piece of work. So without further ado, please join me in welcoming Naren Ramakrishnan to present this work.
Okay, thank you all. It's good to go second because there are more people in the room. So I am Naren Ramakrishnan. I am presenting this work on behalf of all our authors. And I couldn't resist the opportunity to show you this new fancy building of Virginia Tech, which is right outside Washington, DC. So if you fly in or out of the Reagan Airport, you can't miss our building. So feel free to stop by and see us in person here. So many thanks to the Test of Time Awards Committee, to Jeff and your team. Thanks to KDD, this community that we've been coming to almost every year. To the team members. I couldn't get all my team members on a slide, but Jeff did. And this is the slide he presented. And to IARPA, our sponsor. So before I talk about this work, Jeff asked me to sort of set the stage or provide the context for this research. And a lot of people have questions about, should we be even forecasting civil unrest in the first place? And to answer this question and to sort of again give some backdrop to this, it's good to think about what's really going on in the field in social science, which is called event coding. So in event coding, people take newspaper articles like shown on the right. So these articles came from during the Iraq Gulf War. And so people were reading these newspaper articles and coding them in a structured relational format. And this was called event coding by the social scientists. So if you look at the table on the left, they are organized by date. There's a source country, there's a target country, and sometimes they need not be countries, they could be political parties or actors and so on. And then there's a whole range of verbs connecting these two entities. And so you can imagine digesting, volumes of news articles over the years and distilling them into these event records. And then the social scientists used to study these event records to understand patterns, what's going on in the world, which countries are being talked about and in what contexts and so on. So this is the backdrop to our work, and this is at least a decade or 15 years older than our paper. So our paper really did not start this. And so the social scientists, they developed very elaborate taxonomies of events. And so, for example, this is part of a particular code book called Cadenv. And if you look here, they will have very minute and careful distinctions on what types of events have to be encoded and what is included, what is excluded from these events, and so on. And so, as soon as you agree on this code book, then you go back and analyze all these news articles and render them using these code books, and that led to a lot of databases. So these databases are still existing, they're still ongoing. So you can go and check out these databases for work on, from 1950s, 60s, and so on. So it is in this backdrop that we began our project. And if you're interested in the data sets behind it, there's one famous data set called IQs, which is part of the Harvard Dataverse. And today there is also a site called Achla. If you go to Achla, it provides real-time information on conflict across the globe, conflict of various kinds, including but not restricted to civil unrest events. So when we were tasked with studying civil unrest events, we were looking at it, again from this context of event coding. Event coding was only using news articles, but at the time we began this project, social media was a huge additional ingredient to this. There was a lot of organization, mobilization, chatter, discussions happening on social media. So there was a lot of interest in seeing if social media will provide any value-added benefits over traditional news media in forecasting civil unrest. So in our project, as the title of our project indicates, we only use open source indicators. So this means we only use articles or sources that are available to everybody, including you. We are not surveilling individuals. We are not infiltrating groups. So everything is in the public domain. So which includes news, blogs, social media, lots of economic indicators and so on. And the other thing I want to mention is that we were not tracking individuals. So we were looking at population level footprints. So we deliberately strip personal identifiable information from data. There's a little asterisk next to it. We don't do it all the time. Especially, for example, when the president of a country makes pronouncements, it's very important to note that it's the president who's making these pronouncements. So in cases where the person is an elected official, we do want to take that into account, that this person has a position of authority to make decisions. And likewise, the forecasts we make are at the population level, right? So we're simply making forecasts like, educators are going to protest in this city for this reason, and that's the extent of our forecast. So this was a forecasting project, and like I said, we are very interested in forecasting civil unrest and its drivers. And there's a lot of good users or good reasons to be forecasting protests. For the social scientists, this is a topic of academic interest. They'd like to understand why people protest, what are their priorities, and so on. If you're a traveler, you'd like to know where are the hotspots across the globe. The site like Achla supports those types of alerts. If you're law enforcement, you want to be prepared for these protests, so you want to make sure that there is no disturbance or commotions during the protests. And if you're from various industries, protests can lead to supply chain disruptions, and so that's a reason for you to practice protests. So those are the reasons you might want to forecast protests. Of course, there's a lot of reasons why you should not be forecasting protests. You should not even be engaging in this work. And I encourage you to read the literature on this. There's a lot of interesting work with these counterpoints. I also want to point out this interesting work by Gary King and group that came around the time our paper was published. It's a different group of authors. And what they found was they were looking at social media in China, which is a highly fragmented ecosystem of sites. They're looking at social media then, and they were finding out which posts get censored. Okay, so the way they did it was they would go and make a post, they would wait for a while, see if it still exists, and then go make another post, see if it exists, and so on. And they try to figure out what was the rationale behind which posts get deleted and which do not. And you'll be surprised at the results. Your post won't get deleted if you criticize the government, right? So you can criticize the government all you want, the post won't get deleted, but the moment the criticism turns to collective action or organization, that's when they start getting deleted. And there's a lot of work in the social science literature on how governments monitor social media to understand everything from, who's being corrupt, who's, what are the grievances of citizens and so on. So there's a lot of work in terms of how social media is actually very actionable. All the insights that you get are actionable both for the citizens and for the government. So anyway, so there's this whole spectrum of work in terms of where we fit in, who are the users of social media and so on. And it was in this context that EMBERS was done. So every time I describe this about EMBERS, people are surprised. This was a live forecasting tournament. What I mean by that is there was no data that was split into training and test and then evaluated on the test data or something, right? So if you want to make a forecast, you better make a forecast for the future, not for the past, right? So I need to make a forecast and I need to email that forecast today ahead of time, and it needs to be time-stamped. And then we wait for the event to happen or not to see whether your forecast is right, right? So this was a project that went for about 4 years. And so that's why I think this project is very interesting, because even today there are very few live forecasting results that I know of. So it's very different from your Kaggle competitions. So that little box that you see, that's what a forecast looks like. And the forecast simply says the date of the event, the location of the event, who's going to protest, why they're going to protest, and some other identifying information, right? So it's pretty high level. And to prove that these forecasts are good, the way IRPA evaluated us was they commissioned another team at MITRE, whose job it was to go through newspapers and code those events, very similar to that Cameo coding that I was talking about. So there is MITRE that was preparing these events as they're reported in newspapers, and we were sending these forecasts, and then they evaluated the forecasts against these events. So if the event was not reported in the newspaper, it did not happen, right? So the newspaper is the ground truth. And so we're really trying to predict what is going to be reported, hence the word beating the news. And to evaluate these forecasts, there are many metrics. I'll talk about those metrics in detail. But if you want to know how well we did, you should see our paper, which was published 2 years after this paper, which is called EMBERS at 4 years. That's why we describe all the things we got right, all the things we missed, and we did miss several things. So it's not a perfect crystal ball. So let me talk about how forecasts are evaluated. So one of the primary figures of merit for a forecast is the lead time. So you create an alert, and you make a forecast, and then you say that the protest is going to happen on this date, and then the newspaper comes along and it reports the protest, but the newspaper actually says the event happened on this date. And so your lead time is the number of days by which you beat the news. Your date quality is how good are you at predicting the actual event date. right? So there are 4 timestamps, and 2 of them are used for lead time, 2 of them are used for the date quality. But this only works if you know which event is to be matched with which alert or forecast, right? So in traditional machine learning, you have rows of data, and for each row you have an expected output and a predicted output. But in forecasting, you're just predicting something, it's out in the air, and some event has happened. And you need to know whether this one was really that, or this was that, and so on, because you're generating hundreds of forecasts, and there are hundreds of events happening. So you really need to figure out which ones ought to be matched with which. So in reality, you have a bipartite matching problem, right? So if you look at our paper, we have some good discrete algorithms folks on our team, and so what they did was they defined the problem as a machine learning problem involving bipartite matchings. So you have a set of events, you have a set of forecasts, and they're time stamped, so you have to respect the temporal order in which they were generated or created. And then you essentially look for a matching between these events and forecasts, and then you see how good it is. And sometimes you can insist on what is called a non-crossing matching, which respects the temporal order in which these forecasts were generated or the events unrolled, and that's another way to do it. So once you create this bipartite matching, then you're ready to score these forecasts. So you score the date, you score the population, you score the event type, the location, and then you combine all these things, and you get something like a GPA on how good your forecast is. And then you compare the actual date and reporting time, and that gives you the lead time. Right? So these are all the metrics that were used. And when we started this project, this, like I said, this was a continuously running 24/7 system. So it's not something where you can just run an algorithm and then submit the results. So we set up the system through our industry partners who are also co-authors on this paper on the EC2 cloud. So we had machines specifically meant to ingest all this data, news, social media, and everything we were doing. We were ingesting about a terabyte of data a day, 10, 15 years back. So at that time, the machine learning tooling was not that well developed as it is today. So a lot of these folks had to develop many of these technologies themselves. The actual pipeline is like a message passing architecture. So all the raw data goes into these models. The models process it, generate new messages. Those messages go to newer models and so on. And you have to keep track of these messages, because finally when the forecast is made, you've got to be able to retrace it back to the original raw data in order to reconstruct something like an audit trail for that forecast. So let me come to the interesting part. This program was set up like a forecasting tournament, like I said. In addition to our team, there were other teams that were funded by IARPA, and we were all generating and sending these forecasts. And whoever won the tournament was declared the winner of this competition. When we started this project, we had a large team of students who came up with very interesting ideas on how to forecast civil unrest. And so we started with a lot of data sources. And one of the first things we did, like a regular machine learning person, is how would you create a very simple baseline model? So it turns out there's a lot of statistical regularity to protests. People tend to protest more on Mondays and Fridays than on Wednesdays and Thursdays, right? It's just statistically that's the pattern. And so you would be able to generate a very baseline approach, just emitting forecasts at certain dates and hoping that they would really meet their target. So that was one of the models we developed. A second model we developed was volume-based model, which essentially looked at indicators of protests in social media and news and seeing when the volume of certain keywords rises over a certain level, and then use that to make a forecast. If you see the word protest in social media, it's too late because the protest has usually happened. So you really have to look for precursors of the protest. So what do people say when they are talking about their discontent, or what leads them to protest and so on. We developed a cascade regression model that looks at what goes viral on Twitter, and then use parameters of these cascades to make predictions of protests. Our social scientists also told us that a lot of protests are planned. For a protest to be successful, you got to announce it well in advance, and you got to mobilize people. So you can actually look for signs of planned protests and so on. And there was another interesting model that our students developed called the dynamic query expansion model. And in this model, we look for entirely new indicators of protests that are very difficult to anticipate. For example, during the time we did our project, there was a protest due to shortage of toilet paper in Venezuela, and it wasn't something that we were looking for. So the dynamic query expansion model was good at picking up on these emerging clusters of keywords and using them to make these forecasts. So we had all these models, each model independently crying wolf, each model looking at different things and generating multiple alert streams. We tuned these models for high precision so that their union gives you high recall. And there's a separate paper if you're interested in how do you take these alert streams and merge them to get the final stream. You can find more details there. So these are the performance results of EMBERS. The top table are the targets they asked us to meet, and the bottom table is the actual performance. And the things we thought were difficult turned out to be easy. The things we thought were easy turned out to be difficult. Lead time turned out to be pretty easy. The quality score was very difficult because you got to get so many facets right. You got to get the location, the who, what, why, when, where, all of them right. But anyway, these results are described in the EMBERS at 4 years paper, and welcome to look at that. There are some events we successfully forecast, which is the Brazilian Spring that happened around the time we had our project. There were Venezuelan student protests. We were able to capture both the time course of these events as well as the spatial spread of these events. And just to quickly summarize, there are many technical innovations in EMBERS from an applied data science point of view that should be of interest to a lot of folks. Like I said, this is the first live forecasting project. It costs a lot of resources to run a project like this, so it's not surprising there's not many follow-ups after this. The loss function is defined over matchings rather than individual rows. I think there's a lot of open potential for research in this space. In fact, I'm now noticing a lot of work in the information extraction literature where people are extracting mentions or events from text and then matching those to ground truth. That's a matching problem again. And then I talked about audit trails, which is now a common feature of many MLOps platforms, and then this idea of merging alert streams. I think each of them have their origins here, but I think they have very good potential outside. So, in terms of the impact of EMBERS, there are many projects today that use open source intelligence, which means they use publicly available data and try to distill them into not necessarily forecast, they distill them into detections or alerts or risk signals or any type of indicator that would be useful for a range of consumers. And so most of the big companies have dashboards and alerting services like this. The social media work we did led to a lot of interest in this population-based listening, which is so these are companies that offer very broad scale social media surveillance, for want of a better word, where they, they promise to gather and process data at a really large scale for specific items of interest. And the general idea of using open source indicators for forecasting has been adapted to numerous domains. In our own projects, in our own groups, there's work that has been done on using this to do cyber attack detection from social media, because a lot of cyber attacks are often reported outside the organization on which the attack happened. So it turns out open source indicators are a good resource for that. We use it for detecting disruptions in transit service, and other groups have used it for other purposes. For example, there's work done on using the same techniques for tracking power outages, for looking at overdoses that are happening, and even detecting cyberbullying on social media. One area that has really taken off in the past decade is in disease forecasting. There's a lot of work, including again by our group, but lots of other groups, and presented at KDD, on using various open source indicators to forecast everything from the flu to COVID to rare diseases and so on. And if you actually look deeper, they have very similar traits. For example, there's work on reading news reports from WHO and picking out events and looking at demographic indicators of who's getting infected, what types of symptoms are they showing, and developing that into a structured format, and then using that for forecasting a range of diseases. So I think open source indicators are going to be very important and relevant for a lot of domains continuing to come. So thank you again. Thanks again to everybody for this recognition. We're glad to have earned it, and I'm happy to take any questions.
Thank you for that excellent talk, Naren. I think having seen the scale of the system you set up, it's now understandable why it required a cast of thousands to make it happen. So have time for questions. Please come to the microphone if you have questions.
Hello. Thank you for the interesting work. I was wondering, you mentioned that sometimes you can basically like some of the unrest is planned. So I was wondering if you have some metrics of how many of the predicted events were already planned, so that you could have got some information. They were completely.
Yeah, I think in general the planned protest detector could detect maybe 30% of the events. The rest were spontaneous events. It's just the statistics of it. I don't know if those numbers will bear today and also across countries. It depends on a lot of factors, right? But in general, for a protest to be successful, people announce it ahead of time. There's a lot of organization going on, and in fact, people, law enforcement uses it to make sure the protest goes by peacefully, right? So there's no disruption. So they make sure there are extra personnel, supporting it, barricades and etc. and so on. So, but about 30 during our time, it was about 30%.
So my question is more like, do you give any consideration to like protests that are small versus like larger protests that have potential to cause like major disruptions, both in like predicting as well as like evaluating?
Yeah.
If so, how?
So that's a good question, and that's sort of one of the things that the social scientists really discuss, right? Like, how do we define categories of protests? Is it a Boolean thing? Is it like slabs of protests and so on? In this particular project, it was called a protest if it had some minimum of 5 to 10 people. I forget what the number was. And again, the yardstick was it reported in the newspaper, right? So the newspapers have their own criteria for determining is this worth reporting on and something, right? So, but that's what we did. But there are other projects that I know where they actually try to predict the number of people, right? And it's also the case that the larger protests sometimes start as smaller ones, they start as distributed ones, and there is a lot of galvanization that goes on behind the scenes. People join the cause, people with slightly different causes merge into a larger protest. So there's a lot of dynamics of protests that people have studied, but in this case, they're all forecast as discrete events. Did it happen? Did it not happen? And so on.
What was your exploratory data analysis like early on, and how is it more currently now that things have stabilized? Are you still looking to find new features, new subjects of protests, or coverage of new languages or different things like that?
Oh, okay. So actually, our project is ended, and we learned that once people call your project a success, they stop funding you. We're not quite working on this particular topic, but like I said, those methods have been adapted to other things. But it is true what you said, which is, if you study, if you're a social scientist or a political scientist studying protests, there's a qualitative shift in what happens every 5 or 6 years, right? So, like things people are protesting about, the types of protests that happen, the mechanisms for organization, they change. So, if we were to do this project again today, it would look very different. Both the statistics and even the data sources and so on. Which is why a lot of those companies that I showed, they focus on very broad, aggregate indicators of risk or instability and so on. But at the granular level, the types of protests, everything changes, right? So, for example, if there's a certain type of protest that happens with a certain level of regularity, it sort of becomes normal. It no longer gets reported, for instance. And then there are really, big events that happen, right? So in the US, we had this No Kings protest some time back, and it's a very different type of protest that happened across the country and so on. So there's a lot of, I would say, drift in how this data and the topic has changed. So you might have to revisit everything we have done in the context of what is happening today. But my political science and social science colleagues will probably have a better answer to your question.
Thanks for the great talk and seeing this work. And so over this time period, you mentioned that news, if it's not the news, then it did happen, but you also have tweets in there as well. So kind of a two-part question, can you describe how you consider the quality of the sources? And to that point, there's one person's protest is another person's riot. So how did you consider what happened during those time frames and those events?
Yeah. So regarding your first question, obviously, the whole thing gets looped up into a machine learning model. So there's one part of our pipeline that uses probabilistic methods to decide whether certain tweets or volumes are actionable. So we never make a prediction, obviously, based on a single tweet, right? Like even if somebody says, okay, I'm going to start a protest, doesn't mean I will. Sometimes it's used metaphorically and so on, right? So all that, I would say, goes under the machine learning part, which is learning to separate signal from noise and so on. Your second question is a more important one, right? It's an ethical question of, but like I said, we are sort of the folks who are surfacing these signals to the top level, saying, okay, there seems to be something happening here. There are ways to use this technology for good. There are ways to use it for, nefarious purposes. That's why I pointed out that line of work by Gary, King, and group. There's a lot of work in how people are using social media, right? And the thing that I learned during this project is that the governments are pretty adept at social media themselves, right? So they are often using social media for what is called agenda setting, right? The famous statement says, the newspapers may not tell you, how to think of something, but they definitely tell you what to be thinking about, right? They set the agenda by their choice of topics and so on. So in the same way, governments are there to, steer the collective population towards thinking about certain types of topics and so on. So that's still a, ongoing line of research.
Time for one last question. Does anybody want to ask the final question of the test of time or session? No takers. Well, please join me in thanking Naren for a fantastic talk and thanking Naren and his many co-authors for a very impactful piece of research.
I'd like to highlight several of them are here in the audience. I can see the first few rows, maybe. So if you're interested, please come and meet us after the talk.